working as an assistant professor, working in MEG at Karolinska, and is the head of the National Facility for Magnetoencephalography.
Thank you. A lot of really complicated and long words. You're going to hear a few more of those. So maybe very briefly to start, how many people here have experience with MEG or feel confident that they could explain how it works? Okay, a few, yeah, good enough. But at least not everyone. So that reassures me to stick with the introduction I have planned. So we're going to look a little bit at what MEG is to start with, from a technical perspective especially, since this is going to be a very technical talk mostly. And then look at how on-scalp MEG differs from conventional MEG. And then have a look at some clinical applications in epilepsy, which is something that I'm specifically interested in. So let's start. Here we go. So MEG stands for magnetoencephalography, a long word that roughly translates to a magnetic brain recording. And basically what we do is we measure the magnetic field that is generated by neural currents in the brain outside of the head. So we record outside of the head. Problem is the fields that we're looking at, or the field that a single neuron generates, is way too weak to be able to measure it outside of the head. But fortunately, the brain is organized in a way that helps us with this. So we have in the cortex these pyramidal cells that are oriented more or less parallel to each other, perpendicular to the cortical surface. And when we have multiple of those activated at the same time, the fields are going to sum up if the current points in the same direction, of course. We need around 10,000 cells or about a square millimeter patch of cortical surface to get a signal that we can actually pick up outside of the head. It's not just this summation, spatial summation, because they're next to each other. It's also temporal summation that's important. I said they have to be active at the same time. That means in practice, on the level of a few milliseconds aligned in time. So neurons produce two kind of currents, primarily the action potentials and postsynaptic potentials. Action potentials are very short, so temporal alignment is much harder. If there's like a jitter of a millisecond or something, they're not going to sum up temporally. And then also we have two opposing current directions in action potential. So they cancel each other out very easily. Postsynaptic potentials, because of this, are the main source of the signals that we're looking at. Same for EEG, by the way. Though there it's also a bit extracellular. So then when we have a strong enough signal, basically what we have to do is put a bunch of sensors around the head and measure the field distribution. Sounds pretty simple, but maybe this gives off a bit of a wrong impression. So we're still looking at really tiny signals. Here you can see the different biomagnetic fields, how they scale. So the heart is somewhere around here, 10 to the minus 10 Tesla. So this is in picotesla or hundreds of picoteslas. And then what we're interested in is somewhere on disorders in the range of femtotesla, 10 to the minus 14, 15. Just as to give you an idea where the Earth field is, so that's like 1 billion times higher. So what we need is really sensitive magnetic field sensors, which we luckily have since around the 60s. The superconducting quantum interference device, another really long word, or a very long abbreviation. So with this, we can get noise levels below what we're actually looking at. So we actually can reach the signal to noise ratio to record. But there's another problem that we're facing. We're not isolated. There's constantly electromagnetic fields around us. Your phones generate a lot of noise. Car driving by, metro is a big problem in a lot of labs. So we need to somehow get rid of this, otherwise it would mask the signal that we're trying to look at. And what we do in practice is we separate the biomagnetic fields, meaning the person. So we put them inside of a shield, something like this. So magnetic shielding uses some special material, so-called mu metal, that basically deflects magnetic fields around instead of letting it through. And in that way, we can get most of the fields removed, or at least reduced enough that we can see a brain response. This is how it looks nowadays. So this is the lab at NUTMEG. You don't really see the room in itself, just the door, because it's kind of built into the wall and touches like all the way to the ceiling. And this is the kind of system that we have. So it looks like this big hair dryer thing that you sit in, where the sensors are inside of this helmet. It's hard to see here, but it also has a 128-channel EG amplifier built in. So then we measure 306 sensors at 102 locations around the head. And we record this at something like 1 to 5 kilohertz. So we get very complex data that we then try to make sense of. In practice, we want to not just look, or in most cases, we don't want to just look at how does the field look like around the head. We want to figure out how does it look like in the brain. So what is the activation that caused this field? And this is done by combining the signal that we get around on this sensor array with structural information, typically in the form of an MR image of the person's head. So then combining these two, we can determine where are the sources that cause this field pattern. It's, of course, much more complicated how to actually get there, but this is not what I'm going to focus on today. We're going to focus more on the technical sides. But what is important is, I mentioned we have something like kilohertz to 5 kilohertz sampling rate, and the signals that, or the neural currents happen at millisecond resolution. So what we can do, which MEG is specifically good at, is looking at how these activations change over time. So we can resolve the activation on the scale of a few milliseconds, not seconds like it is in fMRI, for example. That is the main selling point for MEG, similar to EG, the extremely good temporal resolution. MEG is also considered a bit better in terms of spatial resolution, just because the fields are not as affected by local conductivity changes. It's completely non-invasive, so not like MRI where we would apply a field, and much less like invasive EG where you cut open the person's head. So as non-invasive as can be, you're measuring something that is already happening naturally. And you're directly measuring neural activity. So it's not, you don't, again, coming back to fMRI, for example, which is a bit of a comparable method, you indirectly measure the bolt response. Here, you're actually measuring the neural currents. All right. Applications is mainly today in neuroscience. So trying to understand cognitive processes, for example. There's a lot of work in clinical neuroscience as well. So we at NUTMEG specifically have a lot of work on giving up on the mouse. We have a lot of work on Parkinson's disease. So trying to find biomarkers for Parkinson's disease. We heard yesterday a bit about beta bursts. So this is also something we have been working on. And then what I'm specifically interested in terms of applications is the main clinical application today, which is epilepsy. So there the idea is to try, in drug-resistant cases, try to identify where seizures originate. I'm going to talk a little bit more about how that actually looks like towards the end. So just a very brief summary of like the main points of the introduction. We measure the magnetic fields generated by neurocurrents, but they're really small, so we need very sensitive sensors and magnetic shielding. And the main uses are neuroscience and epilepsy. So let's go to on-scalp MEG. Hinted at it in the title, and maybe it's a bit obvious from the name what the idea is, but let's start first from why we want to do this. What is the problem? So here's the system that we're using today. I mentioned that we use these sensors called superconducting quantum interference devices, or SQUIDs. And basically, they are a ring of superconductor that is interrupted by two weak links, so-called Josephson junctions, that you can see here. So superconductivity, for those of you that maybe don't know, you probably heard the name, but maybe are not so familiar, is a state where a material, when it drops below a certain temperature, suddenly goes to zero resistance. So it's kind of like a jump, like you can see here, not like in normal materials, it would just slowly go down. It's, of course, more complicated. There's some more stuff. It's not just a perfect conductor, but that is one of the big features. But what is important is this temperature part. So it needs to go to a certain temperature to be in this state where we can use it as a sensor. And this temperature, in the case of the sensors we use, is around minus 270 degrees Celsius. So very cold. And that means we have to cool our sensors. In order to keep them cold at this temperature, to operate them, we need two things. First, we need some kind of way to cool it down. And then we need to keep it from heating up or cooling down the person's head, of course. So basically, cooling down is done with liquid helium, which is at 4 Kelvin, minus 273, I think, actually, degrees Celsius, so very cold. Also expensive, and a natural resource that's running out. So this is maybe not ideal, but what is worse for the MEG side of it is that we need some kind of insulation around it to keep it at this temperature. This insulation, you can see here, so this is how it looks like in a current system. The insulation is a combination of this specific foil that is a very good insulator against radiation mostly, and then a thick vacuum that is the main insulation. Thick meaning something like 2 centimeters. So this is then to the inner surface of the helmet. Then you have another centimeter or more to the actual brain, which is where our sources are. Why is that a problem? So if you look at the magnetic field strength as a function of distance from the source, so this is the purple line here, you see that it drops off very quickly. So the further we are away from the source, meaning the brain, the lower signal is what we actually get. You can see on the right side, this is for a simple current dipole in the brain, how the field looks like on the scalp surface and on the helmet. And you can see that the amplitude drops quite a lot if we're going out there. On top of that, you might be able to notice here that the field pattern looks much more focal when you're close. So it's not just that the signal becomes weaker, it also spreads more. So it's this very rough pattern versus a very focal dipolar pattern on the surface. This has been quantified a bit more sophisticated than just showing basically this, like measuring the distance between the peaks. So it is actually, or we can actually see that closer to the scalp, there are a lot more higher frequencies in the field patterns. Well, what does this mean? So first of all, we can simulate that if we record closer to the scalp or closer to the brain, we get much more information from the brain. We did some work looking more specifically where this information comes from. You can see especially superficial, which makes sense because that's where the difference makes the most. So if you add 2 centimeters to something very superficial or 2 centimeters to something really deep, the relative changes is much smaller or larger. And then this is something I'm going to come back to later. You also have this thing that the sensor is array is fixed, so the sensor positions are fixed, meaning if you don't fit perfectly into the helmet, some of the sensors are going to be far away. So if you measure a child, for example, in this case, resting the back against the back of the helmet, then the back is going to be much better covered. We can see that here. If we actually manage to properly do measure with all the sensors on the scalp, we would get a much higher information density and covering all of the surface. Still not as much detail in the deeper structures. It's not just more information. What is, I think, one of the most interesting things is that we are expected to get higher spatial resolution. So this is different ways of trying to determine spatial resolution. So the peak position around cortical area, for example, is basically that you put a individual dipole in the brain, then you calculate the signal that the sensors would see and try to go back to source level. So you reconstruct the source based on your signal and then see how much that source spreads, how much area it takes over. And we can see very nicely that if we're measuring closer to the head, we should get a much better spatial resolution. There are mainly 2 sensor types that can do this, that get the sensitivity that we require. So remember, we want something on the order of some tens of femtotesla and can come closer. So one is the high temperature superconductor squid, which is basically the same principle as a squid, just a different material that becomes superconducting at a higher temperature. I mean, this would seem like an obvious thing, then why not just replace all the sensors with those? But they also produce more noise because they are warmer. You can bring them much closer. So this is actually still cryogenic, minus 200 degrees Celsius, which sounds like a lot, but this increase of like 70 degrees compared to conventional squids means that we can reduce this vacuum insulation to something like a millimeter. So from 2 centimeters, suddenly we're at 1 millimeter, which is much easier to handle. Plus liquid nitrogen is much cheaper and simpler to work with. Yes, then the other sensor technology that can be useful for on-scalp MEG is OPMs, optically pumped magnetometers, another long abbreviation. There, the basic principle is that you have this small cell with a gas or some atoms in a gas. It's usually either alkali metals or helium. And then you polarize the atoms in there with a circularly polarized laser and bring them to a state. So this is the pumping. You pump them into a state where the spins are all aligned and then become sensitive to the magnetic field. A bit similar to what you have in an MRI, that you get this spin procession in a externally applied magnetic field, and that you can then detect optically. So either with the same laser beam, just basically measuring the light that comes out, or with a second laser, so-called probe laser. There's a pump laser and a probe laser. It can be a combination, or it can be 2 separate lasers. You can see they're pretty small. the individual sensors, and they're not quite as close as high-TC squids. So the cell, depending on the material, has to be heated. So the alkali vapor cells are usually at around 160 degrees Celsius, and then they have something like 3 millimeter of insulation down here. Helium is in gas form already at room temperature, so it doesn't have to be heated. But those sensors have a bigger cell. So it also has roughly 1 millimeter distance from the outer case, but because it's much bigger, the center of it is also 6 millimeters away. And in this volume, you get an integration. So what you see, the signal that you get out is actually an integration over the whole volume, which is why I'm pointing out here the center and not where the cell begins. So in 2012, I think, more or less at the same time, both these sensor types have been the first to show on-scalp MEG. So some very simple single-channel recordings that as more or less is the same type of recording that was the first MEG recording ever and has since always been as the proof of principle type recording. So it's just eyes open, eyes closed, and you see modulation of alpha activity. Since then, they have developed, of course. So there have been multi-channel recordings. This is, for example, a comparison between conventional MEG, so 102 channel. It was actually done here at KI. And then multiple recordings with a 7-channel system. And that allowed us to localize the activity. So this is somatosensory evoked activity, and then the N20. And you can see that they line up quite nicely. OPMs have developed a little bit faster, and there are already some whole head systems nowadays, and even more sophisticated things like connectivity analysis. The main reason for this fast development is that OPMs have become commercially available. So there's several companies nowadays that offer OPM sensors or systems. And that, of course, drives the development quite fast. I just want to very briefly mention there's 2 more technologies that have recently shown on-scalp MEG, but only this, basically the same type of recording with a single channel. So this is still quite far. If you think about the other 2 technologies, it's like 10 years behind, but something maybe interesting in the future. Again, quick summary, just of the main points. Yeah, maybe I don't have to talk through that, since I think I'm a bit short on time. So let's look at some of the challenges and opportunities that the specific sensor choice brings us, in addition to this more information, higher signal that generally just coming closer brings. So the technical aspects, what do those mean for a practical system? So this is a lot of details now. We don't have to go through each of them individually, but it's mainly the 3 types. And I separated here the alkali, so that's called surf OPMs here, or rubidium surf OPMs, and helium OPMs, just because they have some important technical differences between them. But I think important is this one already that we heard before. Distance, it's quite critical. An interesting thing maybe is that with OPMs, theoretically, you can measure more than one direction in a single sensor. So you can do up to 3 field orientations. So you can get the full vector, basically. That usually comes with an increase in noise. So yeah, maybe not something for every application, but for noise rejection, for example, that can be very interesting. And then this with a sensitive area that in a squid, you really just have a square that you integrate over, meaning that the distance that you have, so it's basically parallel to the scalp surface, and the distance is really just this distance to the sensor, not somewhere in between. All right, let's look quickly at a few things in detail and discuss what this implicates. Yeah, first of all, the noise, of course, is higher. I very quickly mentioned that. This is specifically for high temperature squids and for helium OPMs. So just as a reference, a conventional squid sensor is on the order of 3 femtotesla. So even surf OPM or alkali OPM is quite a bit higher in comparison, but like an order of magnitude, or not an order of magnitude, which the other two are. This is somewhat compensated by this increase in signal. So even with 50 femtotesla, we still see an increase in SNR for superficial areas. Then the dynamic range is something that's especially a problem for the rubidium OPMs. So high-TC squids more or less can do the same as conventional. There's no problem in normal MEG with this. Helium ones also go quite high, 300 nanotesla. In a typical MSR, we have something like 50. So this is more than enough. But the surf OPMs have more on the order of a few nanotesla. That means basically that if we look here at a typical room, we have something like 50 to 100 nanotesla, and then you have some fluctuations on the order of nanotesla. This is not good enough. And a magnetically shielded room, I mentioned, takes or requires some special material, and it's really expensive. So we don't want to get a new room with more of this. That is an option. There's a room in Berlin that has 8 layers of this metal. The typical is 2 or 3. And there you don't need anything. There you can just walk around and measure without any issues. But that is the only room of that type and cost a lot of money. So this is not a solution for a normal lab. So what we have to do is improve the shielding otherwise in an existing room. So one way to do that is basically a type of active shielding. So you have coils that generate specific components of the magnetic field. Typically, you have 3 homogeneous components and then some first order gradients. And you measure the magnetic field that is there and then apply a current to the coils that creates an opposite field to that, basically just cancel it out. Sounds very simple, but of course this is quite complex. You can see here this type of coils. They're very complicated to design and construct. And then because these fluctuations that you can observe in a room, ideally you also want to have a dynamic nulling. So not just turn it on once, calibrate it, and it's good, but basically you keep having to measure the signal and count it. So then looking at the operating temperature, of course, all of them have a much less extreme temperature than conventional squid systems. And this means that we can shrink the system quite a bit down. So the conventional system has this huge dewar on top where helium is in, and it needs a lot of insulation. In all 3 sensor types, we can make a much more compact version of this. And this brings a really new, really useful opportunity, namely that we can make the room smaller. So we don't have to have a huge room anymore that houses this big hairdryer. We can just make this kind of tube that has a few layers of mu metal, and then we put the person in. So those examples are roughly the size of an MRI machine. So lighter, meaning we can move it around. You can see wheels on those. You don't need a special foundation like you need in a current room. And then, of course, they are much cheaper. So for some measurements, for example, epilepsy, this could be a really good opportunity for hospitals. And then I'm trying to indicate here that this is the next point is a little bit less for high TC squids, but also theoretically possible, just hasn't really been done. So because of this lower insulation requirement, we can make the sensors much smaller, and we can even package them individually. That gives the advantage that we can have a scalable system. So you don't have to buy a whole system or nothing. You can have a few channels. You can buy a few sensors, then maybe upgrade at some point or not. Sounds very simple, but I think this might be a pretty important point, because if you combine this with this kind of much cheaper and simpler to accommodate shielding, and then the lack of helium consumption, it means that a system like this can be much more affordable. And just to explain why this is important, currently MEG is not very widespread. There are around 200 MEG systems in the world. Sweden has only one whole head MEG system, which is NATMEG. There's some high TC system, the 7-channel system that I showed in Gothenburg, but otherwise everything is here at Karolinska Institute. And most of the systems are in high-income countries like US, Canada, Europe has a lot of them, and then Japan and Korea. But as far as I know, only 2 middle-income countries have MEG systems and no low-income countries. And specifically in epilepsy, most cases that are not treated enough are in middle and low-income countries. So there's a pretty big lack, and something more affordable maybe could help out. The small sensor package has an additional benefit that I hinted at a little bit before. So if we have again this graph of like distance and the field strength that we measure, right? And now if we look at a child and adult in this helmet, the conventional system, we get 2 centimeters roughly. But in reality, of course, this is not true. We don't have 2 centimeters from the brain of sensors. In reality, this is the minimum, and then the truth is some kind of distribution going from 2 and up. And if we just make a similar system with OPM sensors, so we just shrink down the helmet, we're going to see the same thing. We're not going to get 1 millimeter distance. We're going to get 1 to, I don't know, depending on a child, for example, might have multiple centimeters to some of the sensors. And then the idea is that if we have individual sensors, we can actually adjust them to the individual subject. So bring them to the scalp. In that case, we have something, I'm indicating here, it's not a perfect line. You're still going to have some spread. I mean, you cannot perfectly put it everywhere, but it's going to be much closer to this minimum distance, meaning on average, you have a much shorter distance and a bigger improvement. This is an example of a measurement with OPMs that they did in people with different head sizes, so 2 kids and an adult. It looks quite strange. They used a bike helmet and drilled holes in it, and then they put the OPM sensors in and push them against the scalp surface. There's mostly nowadays 3 different versions of this, what I call personalized arrays. So personalized to the person or to the individual scalp, or 2 approaches maybe. So one is similar to the one we just saw, an adjustable helmet. So you have a fixed helmet with slots where you can adjust the depth. So you just push them as far until they meet the head. Then you can make a helmet just for the person. Basically, then the sensors are fixed in position. This is, for example, a 3D printed one that's based on a face scan of the person or a head scan. And then lastly, you have a flexible cap where you just, similar to EEG, put them on a cap and just start measuring, basically. So they have some different advantages. Of course, the cap is the easiest and simplest to set up, but then you have much more uncertainties about the exact position and orientation. And in a custom-made helmet, for example, you have very good knowledge of the position and orientation, but you need to make a helmet for each person. So that takes a lot of time and effort. So adjustable is then somewhere in between. In all of these systems, you have the problem that you have to figure out where the sensors relative to the head. So generally, this is a problem in MEG. You want to determine where the sources are in the person's head. Skipped something here, yeah. Oh. Basically, you need to determine where the sensors are relative to the scalp in order to determine where the source is in the brain. And in conventional MEG, what you do is you have these small coils that you place on the head, then you digitize them. So basically, you just determine where they are on the surface of the head. And then you activate them during your MEG recording. Basically, you measure then the field that they produce, and you can localize where the coil is inside the scanner. So where is it relative to the sensors? And from that, you can determine where is the head relative to the sensors. So this kind of two-way. Problem is that this is depending on having knowledge of the whole array. So you need to know where the sensors are relative to each other and what orientation they have relative to each other to localize these coils, which is, of course, a problem when you want to adjust the sensors. So what we did there is more or less turn it around, the problem. So if you determine, if you have several coils distributed over your head, and you determine the position orientation of those relative to each other, you can do the inverse. So you, based on the fields that one sensor measures from each coil, you can determine where is the sensor relative to the coils and what orientation does it have relative to the coils. So you can calibrate your sensor array in that way. So this was actually used in combining these multiple recordings that we then managed to do a source localization on. A kind of similar approach that was later developed with the same idea is instead of having these coils that are on your head, you can also use coils around the person. So this is coils that were used for active shielding. You can actually use the fields that they generate, the field patterns, and from that determine where the sensors are inside of the shield. Works quite well if you have good coils. So it's quite dependent on how well those are calibrated. Another big thing that comes with these small sensor packages is the systems become really light, and you have them now mounted to your head. It's all just a bunch of small sensors, so you can move your head around, right? It's not this big thing that is fixed in place. And this has actually been shown, so this was the first time there was playing ping pong during a MEG scan. There was a video of it, and the head was very stiff, so it was very limited movement. But in a later work, they actually managed to have a person standing and moving around, which is quite impressive because there is a big problem that you get when you want to do something movable. And that is that you don't have zero field inside of MSR. I mentioned there's still a bit of field left, right? So if you imagine you have a sensor that measures in a certain direction, this is the field, this is your sensor, for example, and now you rotate your sensor. Suddenly the field that it's experiencing is different, the field that it measures. So this was a test where they then moved around the sensor signal, the helmet And you see very clearly in the sensor signal the movements. This is if you have, for example, a 1 nanotesla field, and then you do just few degrees, you're going to get picotesla changes in the field, which is again much higher than what we want to look at. So this is going to mask the signal you want to look at. Which means we need some very sophisticated setups to try to remove this extra field that you would pick up by moving around. So this uses like complex matrix coils together with cameras that detect where the person is, and then tries to minimize the field at the location of the head. And then finally, one interesting thing that the small sensor package brings us, which is we can try some completely new stuff. Normally the sensor is fixed in this helmet. One thing that you can, for example, do is measure fetal heartbeat. This is already possible with normal squid systems, but it requires a specialized scanner for it. And there's, I think, 2 in the world, if even. But with OPMs, for example, it's so small, also with high TC squids, the system is so small, you can just rearrange it. You can just put it on the belly and start measuring. Similar, you can, so in this case, they wanted to record retinal activity, which normally for this retinal measurement, you need to put a wire into the eye to record it, which is not very nice. So this way you can basically just put a bunch of OPMs next to the head and do it completely non-invasively. One brief thing to mention is this bandwidth issue. Surf OPMs have a much shorter bandwidth than the other types of sensors. For most things that we're looking at in MEG, it's more than enough. It's typically we look at below 100 Hertz signals. But one thing of what I mentioned before, which is this co-registration. So when we try to determine where the sensors are, that those coils are activated at a frequency outside of the range that we're interested in. So if we need the whole band, like the 100 Hertz, for looking at neuromagnetic signals, there's nothing left to put those coils in. We have to do some other way. And what has actually been done and seems quite successful is a optical co-registration. So there you basically do a scan of the person's face inside of the helmet. Then you can basically separate that into a part that is the helmet and a part that is the face. And then the face you can align to an MRI of the person's head. So basically just match the face to the face in MRI. And the helmet, you normally have a 3D model because they're all custom made. So you made it normally. So you can just align that to your 3D model and then determine the transformation between those two. I think I'm a little bit late on time, so maybe we go quickly ahead. And now clinical use in epilepsy. So around 1/3 of epilepsy cases are drug resistant, which means that even with like anticonvulsants, you still get seizures. And in many of those cases, it's possible to surgically remove the area in the brain where the seizure starts, which then leads to either complete improvement, so no more seizures, or a significant reduction. And this requires, of course, determining where is that source, where does the seizure start in the individual patient. Sometimes it's obvious from an MRI that there's a lesion, for example, but in many cases it's not. And then we need to do some other types of non-invasive tests normally. And in some cases also as a last thing, invasive, so intracranial EEG, to confirm that this is really where the seizure starts. And MEG is used especially in some of the harder cases, to try to determine this location, and then also to guide where to put intracranial electrodes, because of course intracranial electrodes, you cannot like fill your whole brain with electrodes. You want to as few as possible. So if you already know where you expect the location to be, that makes your life much easier and reduces risks to the patient. Typically, scans in the MEG system are relatively short. So it's not like EG where you just keep them for days until they have a seizure. So oftentimes it's not possible to record a seizure. Instead, you measure what's called interictal spikes. So that's something seizure-like that doesn't develop into a full seizure, that often happens much more frequent. And then you usually do like a 1 hour recording, collect a few spikes and localize those spikes. And that gives you a good idea of the epileptogenic zone. So we did, we want to use on-scalp MEG for this because, of course, we saw in the beginning, we're expecting higher resolution and more sensitivity. So should be helping us to get better estimates of this epileptogenic zone, and then maybe improve this 70% and gain a bit more. So this was with this 7-channel system that I talked about earlier, so high TC squids. And there we try to recruit patients that have a lot of intellectual activity, so we can be sure within a 1 hour window we're going to get enough events. So Karin Westin, who's a doctor at the Karolinska Hospital, she went through a lot of patients trying to identify someone. She had like 30 patients, and did pre-evaluation on 3, but 2 of them didn't want to do it after we told them like about the technology, that it's a bit experimental and all. So we ended up with 1 patient that we then recorded, first with conventional MEG. And there the idea was mainly, we had very limited coverage. So we do a conventional MEG, localize the source, and then project that onto the scalp. And that will help us in a subsequent measurement to determine where do we have to place our system. You can see here that the location was not ideal because 1 is kind of in the face of the person. So the negative peak, so we went only on 1 location. We aimed here, and then did in the same day conventional MEG plus EEG and on-scalp MEG plus EEG. The idea with EEG is kind of like to give us an idea of how many, or like compare it easier because there might be differences in the number of events that happen during those 2 recordings that are just based on the person had less events. But then we saw very nicely that we had exactly the same amount in EEG and in the 2 recordings, which helps a lot in trying to compare those 2. We got some very clear spikes with on-scalp MEG. There was around 2 times higher amplitude. So that's what we expected, that we get a bigger signal. But then, interestingly, we also saw a lot more events. Even though, since both had the same number of EEG events, we can assume that there was the same amount of events happening. So MEG already got a little bit more, the conventional MEG got a little bit more events than EEG, but we had around 3 times or twice as many as conventional MEG in on-scalp MEG. So that is very encouraging. There was some work more recent doing similar recordings with OPMs, but they have nicely whole head coverage, so they could actually localize it and had pretty good agreement with the localization from conventional MEG, and also saw a quite nice increase in amplitude. It was not possible from this to do the same kind of comparison of number of events, but it's a very encouraging results because, of course, if you have more events, you get a better average and you can better localize. So then we wanted to do a simulation study, looking a bit more at like what are really the capabilities if we had a whole head system. In this case, we chose OPMs for the simulation, but it doesn't make that much difference. And then, so Karin simulated 10 epileptic networks that have this activation pattern, so similar to a real seizure. It starts with a small area that's activated, and then slowly increases. We chose concrete steps that increase, so every 3 seconds, the size of the cortical patch that's activated increases, and then also the activation type changes a little bit, but this is not as important for what we're looking at. Yeah, and you can roughly say if the cortical patch is bigger, then you have a bit bigger signal. It's not exactly a linear relationship because, of course, you can see there that sometimes it goes on both sides. So there's some kind of cancellation happening, but generally higher or larger area means higher signal. And then we looked at a seizure. So 3 seconds is where the seizure begins. And in the on-scalp recordings, we immediately see a very clear signal. You see this high frequency activity at 100 hertz, as it's supposed to be. In conventional MEG, you see nothing. And we actually have to zoom out to 15 seconds. So when it's about 4 times as large cortical patch, until we see a clear signal appearing. This is something that we consistently saw for all of the networks. Basically, we can say that generally with on-scalp, we always detect early activity, which is important because activity can move in the seizure. So it's not that it just, you have a fixed point and then it starts increasing. Sometimes the activity moves around as well. So the earlier you are, the closer you are to the actual seizure onset. This is reflected in this detection to seizure onset zone distance. So this is localizing the first activity that you see in each of the systems. And the accuracy at localizing that was actually very comparable, but the later activity is further away from the true seizure onset. So that means that this later has a much worse localization accuracy of the seizure onset. We want to try this, of course, now with a real system. And Daniel, seen here, got some funding a few years ago to buy a whole head system. And last year, we actually then purchased a 128 sensor system from Fieldline together with active shielding. So we're excited to start using that and measuring some epilepsy patients, hopefully more than one this time. Unfortunately, it's been delayed, so I cannot show you any results from this, but we started a collaboration with a lot of people. So we're trying to basically cover all aspects of this. So we want to be able to find patients. So we have neurophysiologists and epileptologists helping us with the recruitment, neurosurgeons, because we want to see the outcome. So there's not really a gold standard for determining how good have you localized the seizure onset zone. The only thing you can say, if it was surgically removed, did the seizures stop? Then you know it was somewhere within the resection area. And then the idea for that is that we're going to measure something like 20 patients a year that are planned to undergo also invasive recording, so SEEG. Also as kind of like a comparison, because with the SEEG, we can see clearer if there is a source there, if the placement is right. That's a bit, yeah. But typically, it's a much surer way of knowing what is truly there, where's the true location. And then we're going to try to localize the seizure onset zone. Maybe interesting is that the idea is also to record 7 Tesla MRIs at the MRC center or MR center at KI, which might help us detect lesions that wouldn't have been seen with conventional MRI, but also might help us to get a better resolution just by having a more accurate structure. In addition to this, kind of doing standard recordings, we also want to do some recordings specifically aimed at measuring seizures. So there, the idea is that each subject gets a personalized helmet that is free to move. The other one, there was a fixed helmet. I don't know if that was visible. Here in the back, it's fixed. That the idea is mostly that by increasing the patient comfort, you can let them, or you can measure them much longer. Because if you're just sitting still in your chair, it gets uncomfortable after a while. So then if we measure several hours and then find the right patients, we should be able to measure some seizures. Yes, I think I'm a bit over time, so maybe I'm just gonna finish with that, and thank you for your attention.
All right, so let's some quick questions. Yeah.
Great. Thank you. Super interesting talk. And I can see a lot of applications in clinics and how in research it can open like new avenues, like study motor control and things like this. But thinking of like more classical perceptual experiments in which people are studying just vision or auditory processing, which would be the selling points for you? Can you really like cut the length of an experiment to half or so?
This moment, no, I don't think so. It's basically that you should be able to have more confidence in your localization by being a bit more accurate. I don't think the increase in, so as I mentioned, they have worse noise. So the SNR gain is not as high as the signal gain. So cutting your experiment in half, I don't think that is possible for now, at least. It's more than hoping to see something that you could not have observed. So small signals, something, then signals from regions that are usually not well covered. This Lau Andersen from Denmark, he's very interested in trying with our system to do cerebellar measurements, because that's typically not well covered. But you can arrange your sensors however you want. So you can put sensors in the face, you can put them further down the neck, get coverage somewhere where typically you wouldn't have had it. Yeah, I think that's mostly, if you're looking at a signal where you know you can pick it up, I don't think you can significant from it.
And how much better is localization compared to standard MEG?
Good question. I mean, in simulations, you have it, I think it was like a half on the like more superficial areas, half the area, basically that your source would spread. So factor of 2, but it depends totally on the individual position. So that is what why there was quite a lot of simulation work being done by different groups, and they all go through a number of different metrics, because there's no simple answer to that. The answer is it depends.
Thank you.
Right, I can go for one maybe. So I was wondering a little bit like how well does these MEG correlate to fMRI? I mean, obviously there's much longer time spans for MEG, but can you at least like see that okay, this is the same areas that are activated and stuff?
Oftentimes, yeah, you can see the same areas being activated. But so I'm not an expert in fMRI, but my understanding is that you may need a bit different design of your experiment to get a good fMRI signal from a specific source. So you might not see everything that lights up in MEG might light up in fMRI.
Mm.
But you should at least see everything that you see in fMRI also appearing in MEG.
Yeah.
If you have very short activation, then that's not repeatedly activated, you might not see it.
Great. So any other questions from Zoom? Maybe?
a question. Maybe I can ask, what's your opinion on how long it will take to go be used more often?
That's a good question. I would hope in the next few years, but I think that MEG is already a bit underused in most clinics. So there are some. Usually, it's a thing. If there is a neurosurgeon that's interested in MEG, then that hospital does a lot of MEG, and if that's not the case, then it does not happen as much. So yeah. I'm not sure how easy it will be to convince medical doctors of doing something new that they are not familiar with and that they don't understand so easily. So I think that will require quite some work to get them to accept it, mostly. I think showing clinical usefulness, that is going to happen in the next years. I mean, it started to happen already with some of those recordings. I would say in the next 5 years, we can have a clear case for clinicians, just if they will accept it. That's beyond my knowledge.
Thanks for the nice talk. How well you think that in comparison to fMRI can detect the activity in the subcortical?
Yeah. Depends on where. Exactly. So I think that fMRI typically is better at localizing deeper structures. So that is definitely an advantage. If you're only interested in, or specifically interested in deeper structures, probably fMRI is a better choice. But I would say the best thing is to do both. I mean, they complement each other. One gives you a better, typically better spatial resolution. So fMRI can help the MEG source reconstruction, for example, by determining where do you want to see the signal. And then you can get the temporal aspects from MEG.
Let's thank Christoph.